Swayam Prabha. Digital India. Educated India.
Welcome to the lectures on Engineering Mathematics 1, and this is lecture number 24, and we will be talking about this improper integrals. So, in particular we will discuss today the convergence of improper integrals of type 2, and in the last lecture we have seen this test integral which was a to b and 1 over x minus a power p. So, this is the improper integral of type 2, because this integrand is unbounded when x goes to this a. So, this integral which is the test integral, and today we will use this integral to prove the convergence of other integrals, and this integral converges when p is less than 1, that is strictly less than 1, and this integral diverges if this p is greater than or equal to 1. So, to start with, so we have again to remind, we have this type 2 integrals, the improper integral, and we will be using this notation which says that this a plus this notation means this f x becomes unbounded when x goes to a. So, this will be the notation used when we used here b minus, for example, that means this f becomes unbounded when x goes to b. So, for the case when we have this integral where f x becomes unbounded as x goes to b, in that case we will deal again this integral similar to this type of integral by just this substitution. So, if we substitute here x is equal to b minus t. So, if we substitute x is equal to b minus t, so in that case this integral will become this f and this b minus t, and this dx will be minus dt. So, with minus sign, and then when x is a, so this t will become b minus a, and this when x is b minus, so this will become 0. So, this will change the limit, and we will get this 0 plus to b minus a and then f x dx. So, this will be the integral which we will be considering again, that f x is unbounded when x goes to this 0. So, in this situation, so we will be considering this integral which is again of this nature, which we take as the standard for the discussion, that f your integrand is bounded when the argument is going to the lower limit. So, in this case here when t is approaching to 0, so this is becoming unbounded. So, the same situation like we have in the above integral, that this f x is unbounded when x goes to a from the right hand side. So, moving now to the next, we have the comparison test similar to the one which we have already discussed in previous lecture for integral type 1. And in this case again we suppose that we have this inequality for the values of the function between this a to b. So, this f is taking non-negative values and g is taking larger values than f, and in that case we have that if this g, the bigger one here, the g is taking larger values. So, if this integral a to b g x dx this converges, then naturally the integral which where this integrand is taking the lower values than the g, this will also converge. Second, we can also conclude out of this relation that if g integral over this g diverges, so the g will diverge if the integral, the smaller one f x dx, if it diverges. So, since this f is taking the lower values than the g, so if this integral diverges, so naturally this integral the value is supposed to be bigger than this integral. So, definitely this will also diverge. So, it is a simple comparison test, but very useful for deciding the behavior of such improper integrals. There is another test here, which is we call comparison test 2, or it is called the limit test also, limit comparison test. And in this case, again we consider this semi inequality that f is taking non-negative values and g is taking larger values than f. So, in that case we compute this limit, which is x approaches to a plus, because our problem was when x approaching to a. So, we take this ratio here f x over g x, and we have to find for what g we are getting this conclusion here. So, we take another function based on the given function f. This will be rather clear when we discuss the examples. So, in this case we will choose some g for given f, or the other way around, and compute this limit. Suppose this limit is coming to be k, then based on the value of k we can decide the nature of the integral for the given nature of the other integral. So, here for example, if k is not equal to 0. So, if we are getting this non-zero number as the limit. So, in that case both the integrals, meaning this a to b this f x dx and this a to b g x dx will behave the same, and the reason is clear that when x goes to a, this ratio is a non-zero number. That means they behave the same as x approaches to a, and then their integral will also either both will diverge or both will converge in this case, and this is very useful. And most of the examples exactly we use this conclusion that this j k which we got after this limit of this ratio, and then either depending on this test integral whether that converges or that diverges the other integral, the behavior of the other integral we can conclude. Further, if we get for example, this k to be 0. So, in this case what is happening, that means this g is growing much faster and perhaps going to infinity than this f x. So, we got this 0. So, it seems that g is having larger values as x approaches to a. So, if this integral converges in this case, this g integral, then we can tell that this integral f will also converge because of this limit here. This g will be growing faster, and that is the reason here we are getting this 0, and in that case if this g converges, the f will also converge. So, without the proof we can just by intuition we can feel that these results hold. Again this is the other way around, that if k is 0, so sorry k is infinity. So, in this case this f x is approaching to infinity, is getting unbounded faster than this g function, and if this g function diverges here. So, if this g diverges, we can conclude that the other integral, which is a to b f x dx, that also diverges. So, with this simple test we can discuss many examples where based on the integral which we have just discussed, this test integral. So, this is going to be very useful. There was another Dirichlet test for type 1 integral we have discussed, and again we have a parallel test here also, which is more or less the same, that if this f integral is uniformly bounded, that means for any b here greater than a, we can bound this by some constant for any epsilon positive. In that case further, if we assume that another function g is monotone and bounded and approaching to 0 as x approaching to this a end, and then this Dirichlet test concludes that this integral a to b taking this product f x g x also converges. So, this Dirichlet test is also useful when we have this kind of product of two integrals, and one we know that this is monotone and this is bounded also approaching to 0, and the other one here this integral is uniformly bounded. So, in that case we can use this Dirichlet test to prove the convergence of this when we have in the integrand, this product. For example, we want to test the convergence of this integral 0 to 3 and dx 3 minus x square root x square plus 1. So, if you want to test the convergence of this integral, then we should note first that the integrand is unbounded at the upper end. So, we are not as per our earlier discussion that we are talking about, I mean, though similarly we can deal when we have this integral is becoming unbounded at the upper bound, but the other way we can just convert it by a suitable substitution to again, so that our integrand is going to unbounded when we are approaching to this lower boundary of the integral. So, by substituting this 3 minus x is equal to t. So, if we substitute this one 3 minus x is equal to t, and that will implies that dx is equal to minus dt, and this our integral will become. So, when x was 0, this t is 3, and when x is 3, t is 0 with this dt with minus sign, and then 3 minus x is set to be t, and then we have here x square plus 1. So, x is 3 minus t whole square plus 1. So, that will be the integral, and then making this plus here, this will be 0 and this will become 3. So, we have the integral 0 to 3 dt over t and 3 minus t square plus 1. So, having this is equal to this 0 to 3 dt over t 3 minus t square plus 1, we can now talk about the convergence of this integral, and now our integrand here is getting unbounded when this t is going to 0. So, at the lower end of the integral. So, we take now for the comparison this function g t is equal to 1 over t. So, we take 1 over t, and the reason why we are taking 1 over t is clear. In this case, when we have this function, so our integrand was f t here 1 over t square root and this 3 minus t whole square plus 1. So, this was the integrand, and as t approaching to 0. So, as t approaching to 0, where is the problem? This 1 over t is creating problem. Here there is absolutely no issues, this square root when t approaching to 0 is bounded. So, this function is getting unbounded because of this 1 over t. So, that means this behavior when t approaching to 0 is set by this 1 over t. So, we will choose therefore, this function g t as 1 over t. So, that is the reason we have taken here this function 1 over t. By taking this one, now we can compute this limit as t approaching to 0 f t over g t. So, this f t is 1 over t and square root this 3 minus t square plus 1, and then g t will be again 1 over t. So, this t will get cancelled, and then in that case when t approaches to 0, we will get 1 over square root 10. So, that case this integral 0 to 3 dx over 3 minus x square root x square plus 1, this diverges because this integral here 1 over t, when we take this integral, because we are going to now compare with this integral g t, because this test says when limit is a non-zero number, this is a non-zero number here, then both the integrals, both means the one is we have this 0 to 3 here 1 over t dt. So, this integral and this integral which we are testing for the convergence, and originally this was in the form of x given by this function here. So, since this integral which we are comparing with 1 over t, this integral diverges. So, if this integral diverges, then this integral will also diverge, and naturally the given integral this dx over 3 minus x x square plus 1 will also diverge. So, by simple this comparison test, we are able to tell without explicitly computing the value of the integral that this integral diverges. Now, we will test the convergence of this integral, where we have pi to 4 pi and sin x over cube root x minus pi dx. So, now we have this problem again when x is approaching to infinity, this integrand is approaching to is getting unbounded, and now we will discuss the convergence here. So, here it is rather easy to see that if we take even the absolute value of the integrand, and we have discussed already in the last lecture, which is called the absolute convergence. So, if we take the absolute value of this integrand, and even though that integral converges, we call that the integral converges absolutely. So, in this case, even we take this absolute value of the integrand, and this is bounded by 1 over, because this sin x is bounded by 1. So, this integral, this absolute value is bounded by 1 over the cube root of x minus pi, and in this case when we have this, so and we know about from the test integral how this integral behaves. So, this integral 0 to pi 1 over this cube root x minus pi dx, this converges because the power is 1 by 3, which is less than 1. So, this integral converges for any power here x minus p, x minus pi power, any power here less than 1, this integral converges. So, here we have this power 1 by 3. So, this converges, and in that case we have that this integral pi to 4 pi sin x over this converges absolutely. So, we have the absolute convergence here, and this is that means definitely this integral converges because we have the absolute convergence. So, absolute convergence implies the convergence of the integral. Now, if we have the improper integrals of third kind, so just to recall what was the improper integral of third kind, it was a mixture of the integral of kind 1 and kind 2. So, we have for example, we have this integral 1 to infinity 1 over x square root x minus 1 dx. So, we have both the cases here, we do see this infinity in the limit of the integral, and also when x is approaching to 1, this integrand is getting unbounded. So, we have the integral of type 1 as well as type 2. So, such improper integrals of we can express in terms of the improper integrals of the first and the second kind, and then we can basically evaluate such integrals, or we can talk about the convergence of such integrals. So, in this case we have our integral is 1 to infinity 1 over x square root x minus 1 dx, and this we can break into two integrals. So, in the first one we have taken the limit from 1 to 2. So, this limit 1 to 2, and in the second case then we have taken from 2 to infinity. Now, what happened in the first integral we have no infinity. So, in that case, but this integrand is getting unbounded when x is approaching to 1. So, this is the improper integral of type 2, which we have discussed, and here this is the infinity. Other than this there is no problem, the function is bounded in whole range from 2 to infinity, and this is the improper integral of. So, improper integral of type 1. So, we have break this integral into two parts. The first one is the improper integral of type 2, the second one is an improper integral of type 1, and then we can discuss separately the convergence of each. So, for the convergence we will use this comparison test, and for the first integral here if we discuss first. So, we will take this function 1 over square root x minus 1, and the reason is clear. If we take a look at this integral here, the first integral, in this case we have this integrand 1 over x square root x minus 1, which is getting unbounded when x is approaching to 1. So, this factor here 1 over this square root x minus 1 is creating this unboundedness in the function as x approaching to 1. So, we will compare with the function which is we have taken this here g x or g 1 x as 1 over square root x minus 1. And if we take the ratio of the two here, so f was our integrand. So, here the f x in the first integral was 1 over x and x minus 1. In the second integral, the g x is 1 over square root x minus 1, and if we take this limit f x over g x and then take the limit x approaching to 1, in this case what will happen now? So, limit x approaching to 1 and this f x over g x. So, this 1 over x will survive, the other one will cancel out, 1 over square root x minus 1, and x approaches to 1, this is 1. So, we are getting a non-zero number here as the limit of this ratio. That means, this integral, the given integral and the integral of this g. So, integral 1 to 2 and this 1 over square root x minus 1, they both will behave the same, and we know from the test integral that this integral 1 over square root x minus 1 dx and 1 to 2, this integral converges. So, hence the given integral this also converges. So, this integral converges. We have seen from the comparison test that this integral of type 2 converges. Now, we will look at the second integral. So, for the second integral we will choose the function 1 over x square. The reason is again clear, because here the function, the problem is because of this infinity. So, we will check the behavior of this function as x approaching to infinity, and from there we will take the function g for the comparison. So, if we take this f x here, which was the integral, so 1 over this x and the square root x minus 1. So, it behaves when x approaching to infinity. So, this is like first I will rewrite this 1 over this x square, and here I will take 1 over 1 minus x. So, I am taking this x 1 to this one, and now if we look at the behavior as x approaching to infinity. So, this term here is not creating trouble, because x goes to infinity, this is 1, and so we have this x square. So, the behavior of this function is like 1 over x square as x approaching to infinity. So, we got the function here g as 1 over x square. So, taking this g as 1 over x square, and if we get this limit for the comparison test. So, limit x goes to infinity and this f x over g x. So, the f x was 1 over this x and the square root x minus 1, and then this g x again 1 over x square. So, we have x square there. So, this is limit x goes to infinity, and again we will take this common x. So, x square will get cancelled, and we have 1 minus 1 over x and the square root. So, as x goes to infinity, this will approach to 1. So, we have this limit as 1, and in this case again for the same reason both the integrals will behave the same. So, one this given integral here, and the another one our test integral. What is the test integral? Test integral 2 to infinity with this g function 1 over x square dx, and we know already that this test integral converges. So, this converges. So, this integral converges, and hence the given integral, the second integral which was the type 1 integral, that also converges. So, what we have observed now here, that both the integrals on the right hand side, they both converges by this comparison test. Indeed, now in this case we can also evaluate this function exactly using the same idea by breaking this integral into two parts, where the first integral will be integral of type 2, the second will be of integral type 1, and then we can evaluate each one. Or we can consider now this integral, the same idea that we have avoided here this 1 by taking this 1 plus epsilon, and the upper limit which was infinity we have replaced by a number r, a large number r, and taking this 1 over x and this x minus 1 dx. Now, we will evaluate first this integral, because it is a proper integral. We have no problem at the lower end and also at the upper end. So, here we will substitute this square root x minus 1 to t, and then we can easily evaluate this integral. So, by doing this substitution, so we have substituted this x minus 1 is equal to t square. That means, we have this dx is equal to 2 t and dt. So, in this case this integral, so if we talk about this indefinite integral. So, 1 over the x is replaced by 1 plus t square now, and this is square root x minus 1 is replaced by t, and this dx by 2 t into dt. So, this t gets cancelled and this integral becomes just 2 over 1 plus t square dt, which we can integrate. So, this is 2 and tan inverse t. So, that is the value of the integral, and now we can put that limit back. So, first this x. So, here 2 tan inverse and the t was square root x minus 1 x minus 1. So, and now the limit from 1 plus epsilon to r. So, putting these limits here now, we got 2 and this tan inverse the square root r minus 1 and then minus the tan inverse, and this x is replaced by 1 plus epsilon. So, 1 gets cancelled and we get a square root of epsilon. So, this is the value of the integral, the given integral, which is given here, the 2 times the tan inverse r minus 1 with the square root and minus tan inverse epsilon. So, with this now we can approach to the given integral. So, in this case this integral here 1 to infinity 1 over x and square root x minus 1 dx we will get when we take the limit this epsilon to 0 and r to infinity. So, in this integral the value of this integral we will pass the limit as r approaching to infinity and epsilon approaches to 0. So, when r approaches to infinity, you note that here r approaches to infinity, tan inverse this infinity, which will become pi by 2 and minus this tan inverse when this epsilon approaches to 0. So, tan inverse 0, that will become 0. So, we have because of this pi by 2 and 2 times. So, this value will be just pi. So, again not. So, this is here tan inverse pi by tan inverse infinity. So, that will be pi by 2 and this is minus 0 and then we have here 2 times. So, therefore, we got this pi here. So, the value of this integral is pi, and we have seen before as well without evaluating the value that this is a convergent integral. And just a remark here that one needs to be careful to evaluate the improper integrals where the integrand is not defined or it is not bounded at an interior point of the range of the integral. So, if we have a point, not the end point, if we have a point in the middle where the integral is getting integrand is unbounded or it is not defined, we have to be very careful for the evaluation. So, suppose we have this integral a to b f x dx, and further we let that f x is unbounded at a point c where the c is a point between a and b. So, in this case this f x is getting unbounded somewhere at the point c, which is in the range of this integral, and then we have to break this at that point. So, a to c f x dx and then c to b f x dx. Now, we have these two integrals of type 2 integral. So, here this is getting unbounded when x approaching to c, and this is also getting unbounded when x approaching to c. So, there are two ways now one can think of getting this limit. One is like we introduced is epsilon, and epsilon we take the limit as it goes to 0, and we have a to c minus epsilon, and here we have done c plus epsilon to b. So, at these two places we have avoided that point c by c minus epsilon and c plus epsilon. We have taken the same epsilon at both the places. In the second case, which is the correct one for the evaluation, basically we take the epsilon 1 here for the first integral, because these two are the separate improper integrals. So, we should deal differently. So, here we have the limit epsilon 1 to 0 a to c minus epsilon and plus this epsilon to 0 when c plus epsilon 2 to b. So, we have now considered these two integrals differently. Here we have introduced one epsilon and then avoided this point there. So, in the case when we have convergence integrals, So, there is no problem whether you take this one or this one, this will come up the same. So, but in other cases we have the problem here, because this might be a divergent integral and this might be the divergent integral, and in that case the value will differ. So, for instance, we consider the simple problem here -1 to 1 over x cube this dx, and this is equal to -1 to 0 1 over x cube this dx plus 0 to 1 1 over x cube dx. So, if we take these two integrals, in that case if we use this first approach by introducing only one epsilon here. So, what will happen when we compute this 1 over x cube, which will be minus 1 over 2 x square, and putting this limit here -1 to epsilon, we will be getting this here. For the second integral again we will be getting 1 minus 1 over epsilon. So, now in these will cancel out and this limit will be 0 basically. But what will happen if we evaluate separately the first integral from -1 to minus epsilon and then epsilon 2 to 1. In that case none of the integrals here, because we will get exactly this here with epsilon 1, and when epsilon 1 goes to 0 this will be unbounded, this will go to infinity. Similarly, this is also not in convergent integral, this also diverges, and that is the reason we cannot evaluate this here, because both the integrals appearing at this place they diverges and they do not exist. But if we do this mistake here by taking the epsilon at both the places, then the value is coming to be 0. So, coming to the conclusion, so we have these two important comparison tests, which was one here where we take this f x greater than 0 and the g x greater than equal to f x, and then we notice that if this g converges, the bigger one, the natural, this smaller one will also converge, or the other way around, if this smaller one diverges, we can conclude that this the larger one will also diverge. So, we have this comparison test and another this comparison test 2, which was also very important and very useful, where we take another function g and compute this limit, and based on this number k we can conclude the convergence. So, if k is not equal to 0, both the integrals behave the same, and if k is equal to 0, if this g integral converges, the f will also converge, and if k is infinity, which implies that g diverges, so the f will also diverge. So, this was the comparison test 2, and these are the references we have used for preparing the lectures, and thank you very much.